Interesting problem. Let me revisit what we discussed yesterday. So, what is the yesterday's problem? We need to find out max value in each window, right? So that's yesterday's problem. So this is how it is. We have 2, 3, 1, and 5, 7. So let's say this is our window and k equal to 3. So how we did? So we wanted to divide this into 3 windows. So this is the first window, and this is our second window, and this is our third window. Right, so in the first window, if you closely see, the max is 3, and the second window the max is 5. In the third window the max is 7. Right, so uh, how do you want to tackle this? So this we come up with somewhat an optimized solution which can be done through Deque. What is the concept behind it, right? So let's say you have 1, 2, 3, 5 and so on elements, so E1 and E2. So if you closely see, this 5 can be part of E1 window, this 5 can be part of E2 window if k equals 3, right? If k equals 3, yes or no? Let's say k equal to, can be anything, so let's not worry about k. Let's not worry about k. So when you are trying to consider a window, uh, when you are trying to consider a window which is of this, or which is of this, which is of anything, so whatever you have, so before 5 you have elements, right? So you have elements before 5. When you are considering any window including all these elements, so any window including all these elements, and we want to find out a max value, so there is no use of the smallest elements with respect to 5. So that's why what you do, what we try to achieve. So generally you have, this is the concept we try to achieve, right? So you have 1, 2, 3, 5 and so on. So as this 5 is higher than previous elements, so there is no point of maintaining these elements even if it is part of window or if it is not part of the window. Why? Because to get the maximum result, current element is max. So when the current element is max, so this can be max of current window or future window, so there is no use of previous elements because they are smaller. So that's what we did. So what we did, so we keep on adding elements to the Deque. Whenever you are trying to add an element, if the current element is greater than the previous element present in Deque, so we just deleted the previous element and we just added the current element. So the probability of current element, right? So why we deleted previous element? Why? Because the current element is already max than previous element with respect to the window. So the probability of being this current element as max within the current window or in future windows is always high. So that there is no point of maintaining the previous elements. So we just eliminated them. So we make sure that always the Deque first element will be the max value. So somehow we could able to derive it. That you understood, Nale? Or do you want me to?
Yes, Shubham.
Yeah.
That part was clear.
Yeah. Okay, so let's move on. So this is very interesting problem. So let's see how can we tackle this. So you will be given an array. You can say the array is you have 10. Let's say 2 minus 10 and 5 and 20 and k equal to. So this is at 0th index. 0, 1, 2, 3, 4, right? So these are the indexes you have. What is trying to say is generate a subsequences, generate a subsequence. The sum of the subsequence on generated subsequence, return the maximum element sum. The only constraint is whenever you are generating a subsequence, any adjacent element 1 and element 2, these are all called adjacent elements, right? So that the max difference between adjacent elements is always less than or equal to k. So it means, for example, this is j and this is I. So if you see, so the index difference, right, the max index adjacent indexes difference is less than or equal to k. So in this case, k equal to. So let me tell you, so what he is trying to say is, you can generate a subsequence. First of all, what do you mean by subsequence? So what do you mean by subsequence?
So in this case, 10 to minus 10 can be a subsequence because the difference between indexes 2 minus 0 is 2.
Hmm. Yeah, that's what I'm saying. He's saying adjacent elements. Okay, so not, for example, if you see 0, 1, 2, 3, do you think, so you can pick up any two adjacent indexes, the difference should be less than or equal to k. Okay, so if you
Okay.
compare
Yeah.
with 0
Yeah.
to 3, then it is greater than k. It's not about min index or max index, it is all about adjacent indexes. Okay, so that
Yes.
difference is less than or equal to k, so that's fine. What do you mean by subsequence? Let's say you have a b c, so what do you mean by subsequence?
A
So
and B can be subsequence. A and C also can be,
is it a subsequence
yeah,
ac?
A, B. No, A, C can be subset, not a subsequence.
No, no,
Subsequence is
both are
basically
same, both are same. So
adjacent.
subsequence means, yeah, subsequence means you can skip the elements in the middle, but you should maintain the order. You understand? So
Okay.
in this case, I
Okay.
skip this element, but I maintain the order. But CA is not a subsequence. It's not a such subsequence.
Got
Understood?
it.
Uh, so that's what I'm saying. So you can generate a subsequence. Subsequence means you can simply, you can, if you want, you can skip the elements in the middle, but you should maintain the same order, same insertion order. So what the problem statement says, generate a possible subsequence, and where the max difference between the adjacent indexes less than or equal to k, and some of the subsequence elements should be maximum. So we should return that. Let's say, what are the possible subsequent, so one best way is, what is the best thing you can do is, the best thing is you can take up all the positive integers. When you take up all the positive integers, in our case all the positive integers are what, 10 to 5 and 20. 10 is at index 0, what 1 is at index 1, and 5 is at index 3, 4 is at index yeah, 20 is at index 4. If you see any two adjacent indexes, right, the difference is always less than or equal to k, so that's fine, so it is also satisfying. Now pick up all the element sum. So in this case, 17 plus 20, so which is going to be 37. The maximum sum you could generate is 37. Even this is also subsequence. 520 also subsequence. 2 520 also subsequence. Even 10 comma 20 also subsequence. You can skip the elements in the middle, but do you think it is a valid subsequence? It's not, because 10 is at 0th index, 20 is at 4th index. The adjacent index difference is greater than k. So definitely this is not valid subsequence with respect to our input, right? So if he is not giving this condition, right, if the user says don't, if there is no k in the input, the simple answer is you can pick up all the positive integers, simply make a sum of them, then simply return it, right? So based on the condition checked, correct? If there is no k, if there is no k in the input, then you can simply pick up all the positive integers from the given input and return the sum of those elements, which is going to be max sum of the subsequence. But here he has given a k, right? So we need to somehow solve this problem through k, correct now? Problem statement is clear,
Yes.
Ajay? And you see,
Yep.
he has given one more input, minus 1, minus 2, minus 3. So in this case, he has given k equal to. So he just take only one subsequence with minus 1. So this is going to be the max. So if you add any negative value, so which is going to be smaller, that's why you just pick up only one element. And there is one more input. So let's move on. So this is interesting one. So you have 10 minus 2 and minus 10 minus 5 and 20. So what could be the valid here, k equal to? So let's pick up the subsequence as okay, so 10 minus 2 minus 5 and 20. Now if you see, it is at 0th index, so let's say here 0 1 2 3 4, it is at 0, this is at 1, this is at 3, this is at 4, so that max difference is always less than or equal to k. Now if you pick up the sum, so which is going to be 23, so it's a valid subsequence. You may be thinking that I should go with 10 comma 20. So 10 is at 0th index, 20 is at 4th index. So but here the max difference is 4, so which is greater than k, so definitely this is not valid subsequence. So obviously this is the perfect output. So you may think that I go with if you look for any other solution, definitely it will go wrong. You may say that I'll go with 10 minus 5 and 20. So 10 is at 0th index, 5 minus 5 is at third index, and 20 is at 4th index. So this adjacent difference is less than k, but this adjacent difference is greater than k, so that this is not valid. If it is valid, it could have been 25, which is greater than 23, but this is not valid with respect to k. So this is the expected output, right? Now the problem statement is clear. Let's see how do you tackle this. So this is what we have, right? I am at 10 minus 2 minus 10 and minus 5 and 20. Okay, so 0 1 2 3 4. So let's talk about brute force, then we will try to see optimized solutions. So first of all, I am at 0th index. Okay, so let's go over our result array. So this is my result array. So this is also same as my given input, 0 1 2 3 4. So let's see, I am at 0th index. Let's say I pick up only 0. So if I pick up, let's say you have only one subset with 10, and let's say you have k equal to, so you don't have any option, you blindly pick up this 10. Okay, so it means for 0th index you pick up 10. Now when I go to when I go to first index, so this is first index, right? So when I go to first index, so if I include the first index value, then I need to see all possibilities. Okay, so if I include, so this is my first index, the first index value is minus 2. So let's say in the previous index, right? So previous index, it means if you closely see this array, right? So let's say this array is kind of DP array. So this will maintain the max sum you could get by including current index. That's it. So in this case, if you closely see, when I'm at 0, you don't have an option, you blindly take that value. When you are at index 1, you can include index 0 value, because at index 0, what is the max sum you could get? It is present in this DP array, so that you can blindly take that. So 10 minus 2, which is going to be 8. It means if you closely see, if I consider only two elements, if I consider only these two elements, the max sum I could make is 8. Okay, so that's what the answer here. Now let's move on. If I consider index 2, okay, so if I consider index 2, so I have at index 2 I have value minus 10. Okay, perfect. So I have value minus 10 at index 2. Now for index 1 and for index 0, what is the max value you could get? You already know. So let's see what is the max value you could get if you consider index 2. So what you should do, you already know previous problem results. For index 0, for index 1, what is the max value you could get, which is already present here. Now what is the answer? So see all possibilities. Okay, so current value is added with index 0 sum, so that is plus 10, so you got 0. And similarly, current value is added with index 1 sum, so 8 plus 8 minus 10, so which is going to be minus 2. So it means if you closely see, if you include three elements, it means minus 2 comma 10. This is what, 10 minus 2 comma minus 10, right? So if you include three elements, then the sum is minus 2. If you include only these two elements, then sum is 0. So the maximum of including current element, what is the maximum sum you could get, which is 0. So 0 is the maximum sum. So how do you get the 0 element? 0 is the maximum sum, first element, and the index 2 element, the sum of these two elements is 0, so that for index 2 the max possible sum you could make is 0. Now let's move on to index 3. So when I'm at index 3, so I am at index 3, so you have value as minus 5. Now I need to see, okay, so let me include, first of all, can I include, when I am at index 3, when I'm at index 3, can I include index 0 value? So when you are at index 3, can you include index 0 value? Because 3 minus 0, so which is going to be 3, so which is greater than k. So definitely you should not include 0th index value, so that you can start from index 1, right? So if you start from index 1, so 1, 2, 3. Okay, so let's move on. Let's move on. I confused it. So let's say you have at index 3, you have value minus 5. Let's see all possible solutions. So for index 3, uh, so if I consider, can I consider index 0 for index 3? So definitely you can't consider index 0. Why? Because 0 to 3, the difference is greater than k, so that you should consider, generally how do you consider, how do you make it? So you are at index 3, so you can max go minus k, so k equal to, so 3 minus 2, so which is going to be 1. It means from first index onwards you can consider the sums for current index 3. So that let's see, if I am at index, so from index, when you are at index 3, you need to see what is the maximum sum you could make. So first go to index 1. At index 1 you have value 8 minus 5, so which is going to be 3. And let's go to index 2. So at index 2 you have 0 and it is minus 5, so which is minus 5. So it means if you consider current element minus 5, if you consider current element minus 5, so the maximum subsequence you could make is 3. Is that correct? Yeah, so the maximum subsequence you could make is 3. Is that correct, buddy? So if I include minus 5, so let's say you have 10, minus 2, minus 10, and minus 5. So these are the elements, right? So 0, 1, 2, 3. So obviously you pick up these two elements and this element. So 10 minus 2 minus 5, so which is going to be 3. So obviously you got maximum sum for index 3, you got the maximum. If you consider current index, which is 3, which is to be part of the result output, so definitely the maximum output you could get is 3. Now let's move on to index 4. So I am at index 4, so let me erase all these. It's a dynamic programming solution, but this way of thinking is very critical. So I am at index 4. So index 4 you have value 20, and you already know the solutions for 0, 1, 2, 3. When you are at index 4, so the minimum index you could reach is 4 minus 2, so which is going to be 2. So from index 2 onwards you should consider. Okay, so at index 4 I have 20, so at index 2 you have 0, so which is going to be 20, and then you will also see the consideration for 0 plus. Next index is 3. At index 3 you have value 3, so consider 3, so which is going to be 23. The maximum you could get here is 23. That's it. So this is your final answer. Is that clear? Algorithm is clear, Ajay? Okay, so what is the time complexity here? What is the time complexity here?
I think we are creating each blocks actually.
So what are we
And we
doing?
go
We
by
are
the sum.
traversing n elements, correct? For each
Yes.
element,
Yes.
how many elements we are going back?
That depends upon the sum actually. If
No. When I am considering current element, right? How many elements we are going back? So when I am at 4, right? From where I started? When I am trying
2.
2, it means what? K, n minus
Basically, we're
k,
trying to
you go
n
n
minus,
minus
yeah.
k back, right? So n minus
steps
k
back, correct?
elements
Yes.
back, right? Correct, na?
Yes.
So,
Yes.
so it somehow, if the k size is really, if the k size is equivalent to n, let's say k size is equivalent to n, then it is going to be n square. So you always go on to zeroth index, right? So it is always going to be n
Correct.
square. So the time complexity here is n into n minus k, so which is equivalent to n square. And
And
what is the
square.
space complexity?
We're taking the same size as of the initial array,
Yeah, so this is DP array, right? So which is of big
DP
O
array,
of n, right? Do
big
you
O of n.
understand this concept? This concept is very critical. If you're able to solve it, then yeah. So this is very critical concept. Let me quickly repeat it. So this is what we did. So 10 minus 2 minus 10, 5 and 20, and we know that these are the indexes. Right? 0, 1, 2, 3, 4 and k equal to. So what is our thought is, so we are going to maintain a DP array. So we are trying to achieve, just a second. అమ్మా క్లాస్ చెప్తున్నాను కలిపి. So we are trying to achieve, so what we do, so we are, for each index, what is the maximum sum, including current index, what is the maximum sum you could make? That's what you want to achieve. So when you are at zeroth index, you don't have any option, you blindly pick up. So when you are when you are at first index, so you can only, if you want to include current, so current element is minus 2. So if you want to include previous one, so this is my previous one. So this is my previous one. So if you want to include previous one, so definitely you can have 10 minus 2, so which is going to be 8. So definitely you get it. Now when you are at index 2, so you want to include, so I am at index 2, I am having value minus 10. So assume that this is current value is the max. Now let's consider, so from index 2, so you can always I minus k times you can go back. It means from index 0. So okay, at index 0, the maximum you could make is 10. 10 minus 10, so which is going to be 0. And then you will try for next one, so which is 8. So 8 minus 10, so which is going to be minus 2. Now you understand that. I feel this is the max answer, so consider that max answer. It means for index 2, the maximum sum you could make is 0. Then let's move on to index 3. So when I move on to index 3, initial max is it minus 5? Yes, it is minus 5. So it is minus 5. So initial max is minus 5. Now you can traverse I minus k. It means from index 1 you can start. So at index 1 you already know what is the maximum sum you could make. So 8 minus 5, which is 3. Then index 2 you have 0. So 0 minus 5, which is minus 5. The maximum sum you could make is 3, so that you added 3 here. Now I am at index 4. Then I can traverse n minus k, so it means I can start from index 2. So from index 2 you get 0. So 0 plus index 4 you have value 20, so which is 20. Index 3 you have 3, so 3 plus 20, which is going to be 23. So 23 is your answer. So what you are trying to do, you break down the possible solution. So you try to achieve this problem with bottom up approach. So for each iteration, for a given index, what is the maximum sum I could make? So till the last index you could see the maximum result. So this is not a optimized code. Now let me write this code, then later we will optimize this. So this is what it is, right? So you have DP array, new integer array of nums dot length. Yeah, so our job is yeah, so DP of, okay, so for int index I equal 0 and I less than, yeah, I less than nums dot length and I plus plus. Now we need to see, right? So definitely initially the max is going to be current value, so which is nums of I. Now what we should do, so we always start from 0. Okay, so we always start j as I minus k. So this we already know. So we, because that's a possible valid index, and we just show j less than I minus 1, or j, what do you say, j less than I, correct? So is that correct, buddy? Is that correct?
Yes.
That's
Yeah,
it.
I
So
minus k, correct. Yeah.
yeah, so I minus k, and it should be less than I, because the current I you are trying to derive on dp, right? So as long as this
Correct.
is fine, then what is your job? You will just find out max equal to math dot max of is it okay, so let's say current current max, current max equal math dot max of current max is the current element is maximum, or adding the current element, adding the current element to the dp of j is maximum, correct, nobody? So this is more critical. So finally you will add dp of I is equal current max, done. Then finally you will just return, so dp of nums dot length minus 1. That's it. In the last index you have the value.
The actual result. Yeah.
What happened? Minus 2. Why it went to minus 2? J plus plus I plus plus db of j. Okay. The problem is less than is always wrong. I minus k. Yeah. What you do here? Mm, mm, mm. This condition check is wrong, so let's correct that. So this is what we are trying to do, right? So when I is at 0, okay, so we need to find till where it should go. So what we can do, we can make yeah, let me do that. So you have j, right? So they, j can be math dot min of, it should not be negative, either it is 0 or I minus k. So whichever is, if it is 0, it always be 0, math dot max. Okay,
Max, yeah, correct.
so
Yeah.
that way it will work. I will just replace this condition here. Yeah. So yeah, so what is a mistake here? You have, in this case, uh, you always end up having he has given k equal to 1, so that you don't go anywhere. So tell me what is a mistake here. This guy has given k equal to 1, so that it cannot compare with the previous element, right? So obviously
Correct.
it always have, in the last one you always have last value. So what is your job is, better you will always make a global max, so which is going to be integer dot min value. Okay, so that it doesn't depend on k. So max
Okay.
equal,
It doesn't depend on the last element. We
yeah,
can
yeah,
keep the
max
max in
comma
the global part.
current max, yeah. Somehow you can do that, so you can simply return this max. That way it will take care of everything. Okay, so if I submit, I think definitely it will fail because of the n square. Let's see. Yeah, it will definitely give time limit. So that's it. So it was given time limit exceeded. Somehow this code is correct, but the problem is the complexity, right? The time complexity is the problem. Now let's see how do you approach. But this approach, right? This approach is highly useful when we try to apply the same concept on hashing. So you can make these things very beautiful. You can avoid the time complexity, but that we will solve in future problems, but this approach is very good. Now let's understand what is the mistake we are doing, and we will try to address that. Okay, so what is the mistake we are doing here? So let's see here. Okay, so this is the input, right? Ajay, can you tell me what is the mistake we are doing here?
Are we considering the same window again and again here?
No, we are not doing that because we are always
Because
going
we are
on.
going by the loop
We are always going on I minus k, right?
I minus k. Correct.
We are not considering previous thing. What are we trying to do? So in this case, what is the mistakes we are? What is the mistake we are trying to achieve? What is the mistake we are trying to do? So let me. So initially you have value 10, right? Then I got value 8. Then I got value 0. How I got value 0? I compare with both the elements, right? It means
Yes.
I have compared with previous I minus k results, right? Yes or no?
Right.
Now when I got here, I got value 3, right? So if you closely see here, this is more critical observation so that you can understand how the improvement we can do it. So initially there is no option for the first element, so you got value 10, perfect. And for the second element also, you have only one option, so you got value 8. Now to the third element, right? So this is the third element. Third element, I need to consider previous k elements. Previous k elements are 2. Out of these two elements, if I could able to pick max one, right, I can easily get the perfect result, right? Right? Out of these two elements, which is max? 10, na? Yes or no?
Yes.
So if I can easily
Yes.
get 0. Now when I go to minus 5, these two are the max element. These two are the k elements to consider. Out of these two k elements, if I am able to figure out what is the max, what is the max out of it? 8, na? So if it is 8, 8 minus 5, so which is going to be 3. Now when I am at 20, so these two are the last k elements. Out of these two, sorry, when I am at 20, so these two are the last two elements. Out of these two, if I could able to get max value, then I can simply add, so which is going to be 23, correct? Yes or no?
Correct.
Perfect. So now you understand that. Now you understand that we always need to take care of max element, right? So within that window, if I am able to have a max value, done, I can able to solve this solution, correct? Correct, na?
Yes.
So how do you do that? There are multiple ways to do that. Okay, so this is what causing the.
I mean, when we are inserting that latest element, can't we keep track of what is the previous max?
Yeah, let
Yeah,
me.
yeah. In this,
Yeah,
yeah.
let me explain what are the possible solutions you could think of. One thing for sure, within a given window, within a given window, we need a max element, correct? Right?
Yes.
Within a given window, we need a max element. So one thing you could think of is heap. Heap is heap is a data structure. It always max heap. So you can have max heap. So max heap will always return the max element in constant time. So one thing you can think of max heap, but we didn't learn about max heap. So for now we will pause it. Now let's say, do you have any other solution? Do you have any other solution? Do you have any other solution? What is the other
So in a way
solution to
we
find
can
out max
keep
element? Don't think about Deque. We will talk about that.
Okay.
So okay, you have max heap, so somehow it returns the max element in constant time, but you can't able to do that. You can't able to do that because we didn't know about it. What could be other thing? Sorting, right?
Sorting, yes.
So sorting, right? But if you try to sort every time, so this is going to be n into n log n,
N log n.
or k log k. So you can say k elements. Then you keep on sort k elements. Then for n elements there is a k window, so it is going to be k log k, right? So somehow you can do through sorting, but it is going to be n into k log k. So it is also almost similar to previous solution, and it is adding extra log k. So now what we do, instead of instead of sorting each time, so we use some kind of technique. So that is what that's what we can do through tree set.
Okay.
So tree set is generally do the sorting. Uh, so, but the advantage you could get is, if you don't use tree set, if you use normal sorting, and if you have x elements, xk elements, first you should sort all the xk elements, then get the last element, which is the max, right? But if you are using tree set, the advantage you could get is, it doesn't know, it applies some beautiful algorithm, and it makes sure that the last entry and first entry you could get in constant time. So when it is a tree set, if it is a tree set, the last entry means what? Max value, right?
Max value.
Right, so max value. So the first entry means what? It is a min value. Okay, so you don't need to worry about first entry, but last entry you can get in constant time. So that's the advantage you always get through tree set. Okay, so let's go with the concept of tree set, and let's see how can you do that. Okay, so I have one thing for sure, I must and should maintain the DP array, because I don't know what is the maximum sum I could make. But where is the optimization we are trying to do? Instead of traversing all the n minus k elements in the DP array, all the previous k elements in the DP array, we are trying to achieve that max value in somehow constant time. Let's see how can you do that. So I am having tree set. So this is my DP array. This is my DP array. Now I am having elements as 0, 1, 2, 3 and 4. Okay, so firstly I will have element 10, so as we already know, and it is also present in tree set. And secondly I will have minus 2, so I don't have any option. So in the tree set you have only one element, you just pick it up, then that is going to be 8. Okay, so now I am having 8 in the tree set. Okay, now when you are going on to the third element, correct? When you are going on to the third element, uh, let's say here in the third element, okay, so when you are at third element, so previous two elements are valid, so definitely you will go with the previous two elements. So let's move on. So what is the previous two elements? So the previous two elements are 10 comma 8, which is already present in tree set. What is the max value in the tree set? 10, right? Tree set can
10.
simply return that 10 in constant time now, so that you can get that 10. So 10 minus 10, so which is going to be 0. Now when I am at 3, right? When I am at 3, what is the invalid value, buddy, from the tree set? So it means you have also 0. So when you get current result, you must and should add the current result into tree set.
Tree set.
Okay. Now when
But
you are
before
at
that,
third
we
index,
need to
what
get
is
the
the invalid
max of
value?
10 or 8, right?
Sorry.
Yeah, but before that we need to get the max of 10, 8, right?
That's what we did, right? So what
Yeah.
we did, so when you are here, so I am trying to achieve I am trying to achieve this guy now. At index 2 you have value what, buddy? Minus 10, right? For index 2, previous two elements are valid. So for previous two elements, the maximum results present in DP array, which is also present in Q array, sorry, this one, tree set, correct?
Tree set, yes.
So in the tree set, from the tree set I got what is the maximum? 10. Okay, I got 10. So 10, and current element is 10, so 10 minus 10 is 0, so I'll keep 0 here, and I'll also add 0 here. Now this is more critical. Now I am going on to third index. So when I am going on to third index, I need to consider this element. But when you are at third index, what is the invalid value? For so these two are the valid values, right? Previous k elements are the valid
10 is
valid
the
one,
invalid one.
but 10 is the invalid one, right? So remove that 10 from the tree set first. If you don't remove, that will pop up here, correct?
Correct.
So first, how do you remove? How do you know that? Simply, buddy. So on the DP, this is my current I minus k. So it means current I is 3, k equal 2. So it's 3 minus 2. It is written valid k value. Just say minus 1. So which is going to be dp of 0. At dp of 0, you have value 10. So which will get removed here. You understood?
Oh, yes.
So you just remove it. Now, of course, I have did a mistake. I have done one mistake, but you will figure that out. And this problem will work, but I will tell you. So I'm at index 3. So when I'm at index 3, in the tree set, I have only two elements, 8 and 10. So I pick up the max value 8. So that you got the 8. So once you get 8, 8 minus 5, which is going to be 3. So you will just get 3 here. Now when I'm at 4, which is the invalid value, buddy? Which is the invalid value?
8.
8. It means I minus 4 minus 2 minus 1. So which is going to be 1. So at dp of 1, you have 8, right? So remove 8 from the tree set. Of course, you add this 3 as well. So out of these two, 3 is the maximum value. So that 3 plus 20, so which is going to be 23. So blindly, you will return that 23. Perfect? Understood? Now, what is the mistake we have done here? It's perfect. So it's a valid result. But can you tell me what could be the possible mistake we could make here?
You're taking a tree set which will take care of the max part. It will remove the beginning of the element also.
This is correct, but there is one mistake we have done. If I write the input, let me take the input so that let's see can you able to trace that out or not. I have 10, 10, okay, 10. What else I can do?
You mean when you're taking a tree set, if the elements there are of same values, then which one to delete?
No. Let me take the. I need to seize a valid input, buddy, to make you understand that. So the only problem you could face is, what if you get duplicate maximums? Let's say you have, this is the good result, buddy. So I have 10, 0, and minus 10. Minus 10 and 10, 0, minus 10 and plus 10. So what is the max result here? No, it should be 20, right? 10, 0, 10.
Sorry.
It should be 20,
10,
right?
0,
Because
10,
0, 1, 3,
yeah.
so difference
and k is 2, okay.
Yeah, so k is 2. Now if you apply the same trick here, it will fail. So how it will fail, tell me.
Let's consider the DP tree set. I think somewhere in the taking out the element from tree set, that would duplicate
Can you
number.
quickly tell me, as you know the algorithm? So this is my tree set, okay? Let's say I go with tree set. So initially you will have 10 only. So here also 10, correct? Correct,
Yes.
Now later you will have,
Yes.
so you will get 10 only. I need to add 10 here, right?
Yes.
But this is gone, right? It doesn't tell a duplicate things, right? It is a tree set. So this is gone. Now when I go to minus 10, it will give plus 10. Okay, so when I go to minus 10, so obviously it will give plus 10, so it is going to be 0. Now when I go to here, if you closely see, when I'm at index 3, okay, so it is going to remove this one, right? Zeroth index value. So zeroth index value
remove
10.
the
10. So there is no 10 in the tree set. Tree set is empty
correct.
now. So actually ideally there
Correct.
should be one 10, right? This 10 was deleted, but this 10 should be present here, right? Now how do you
Correct.
solve it? How do you solve it?
Can we take a map?
Which map? Which
we take a
map?
hash map.
Hash map
Hash
doesn't
it.
sort it right. Doesn't sort it right.
Yeah. Correct.
Tree map.
Tree map. Okay.
That's it. So tree map will solve the solution. No? You have key as the sum, value as the count. Then when count is 0, then you remove from the tree map. If count is greater than 0, you keep it from the tree map. Correct, na?
Yes.
So what is the time complexity here?
Same what we had for the tree set in constant time.
Please focus. So what is the time complexity here? Okay, so what is the, so of course you have DP array. Okay, so you have elements in the DP array. What is the size of my tree map? Max size of tree map?
Same as the TP array?
No, we are deleting, right? When we are extending, we are deleting the elements or not?
Alright, we are removing element also, yeah, correct.
So what could be the max size of tree map? K only, na?
Yes, based on the window of that
right?
element.
So it means what you are doing, you are trying to add K elements to the tree map, correct? So it means when you add an element to the tree map, it will take log n time. So because you have K elements, which is going to be log K, correct?
Yes.
So it is going to take log K, but for each so in the tree map you have log K elements. But the thing is, from the tree map, if you want to pick up max element, it is always be constant time. Understood? Tree map,
yes.
Picking up a max element is always going to be constant time. So let's say in worst case you can say it is n into log k. Do you agree?
Yes.
So it's a log k, right? Because you might be thinking that okay, so how it can be log k? The problem is, let's say you have k minus 1 elements in the tree map, and now you are at kth element. Now you add kth element again to the tree map, right? So that this kth element will take log k time to add the data into tree map. So that's how for n elements it is going to be log k operation. So it is n log k. So what is the space complexity?
Order of k.
Yes,
because that many number of elements
for tree
only we
map,
have, right?
and we also take DP array, right?
Yes.
So that is going to be order of n. Okay, so this is very good problem on dynamic programming with hashing. You better solve it. So let me solve that. So what is the improvement we are trying to do here? So I am making use of tree map, so which is of type integer comma and integer, correct?
Yes.
New hash map. So now what is our job? So we will pick up, so this is our elements, right? Now what we do, so we make sure that we remove, we will see that if I minus k minus 1, if it is greater than or equal to 0, it means you have an invalid element, correct? Yes or nobody?
Yes.
So what I should do, I will take that old element. So it is present in DP array. So DP of I minus k minus 1. You will get it from DP array, old element, and you need to remove it from the tree map. So definitely it always present in tree map. So tree map dot get of old element. It will give the count. Okay. I think I could have write this code at last. That's okay. It will give the count. So if count equal to 1, it means it is only single element. Then you can simply remove from the tree map. Correct, nobody?
Yes.
Old element. Otherwise, what is our job? So we can simply make sure that TreeMap dot put off for this old element. You just update count minus 1. This is only the critical test case. That's it. So we are able to handle this. Okay, so this is how it is. Now let's move on. So what we can do now, we need a max value, right? So map dot entry, so it is going to be integer comma integer last value, or max entry, you can say max entry. How do you know that? So how do you get the max entry? So it's all about, generally, let me do that. What you can do, if tree map is empty, okay, if it is if it is empty, then definitely what will happen, buddy, the max, it will return null. Otherwise you will get tree map dot last entry, correct?
Last time. Yes.
Last entry. So if max entry is not equal to null, then so you will always make sure that this is my current max. Current max is always going to be current element, so which is nums of I. And if it is not equal to null, then what is your job? Current max equal current max plus max entry dot get key, because key is the sum and value is the count we try to make, correct now, buddy? Yes or no?
Yes.
Now what is our job? Now what is our job? So that take the current max count. So tree map dot get or default of the current max. If the current max is present, it will return that count, otherwise it will return 0, and for that you will add +1. So I'll write it in single line. So TreeMap dot put off the current max value is going to be TreeMap dot get or default of current max count and +1. Is that clear, buddy? And each time what is your job?
Yes.
So update the max equal math dot max of max comma
Max of.
current max. Correct na?
Mm.
So this is a simple logic only, but the algorithm is somewhat more analytical. I need to
Yeah.
have last entry. What is it? Expected colon. Okay. So what is a mistake? It's TreeMap.
Right.
Null pointer exception is int value. Yeah. Why? Okay. Yeah. What is the mistake we have done? Tell me, please.
What's the input here? We have.
We are getting the value from the DB array.
No, it's failing in the tree map, right? We're getting that element, but in the tree map, that element might not be there.
But it
That
is
key might
always,
not
we
be
are
there.
always adding to the tree map, right? At line number 24. Where are we missing it? Where are we missing it? Are we adding to DP array, buddy?
We are not adding to DP array.
That should be added,
Yeah.
right?
Yeah.
So that's where it is giving 0 here. 0 won't present in tree map. So it will give null pointer. So that's a tricky part. See how it worked. So bad.
Which input?
Okay, so let's see that. Let me get that. Ideally, it should be some of these two elements. Somehow it couldn't able to take these two elements up. Yeah. So tell me, what is a mistake? Tell me what is the mistake, buddy.
Okay, equal to 2, inputs are negative.
So I can tell you the hint. Here is the mistake we have done. We have done. We are blindly updating onto the current max.
Okay.
And if you see the input, you will get it. Very good. So I am here, right? When I am here, what will happen?
Mhm.
When I am here, what is the max value it will return? Minus 5.
401
No, no. When
minus
I
5,
am,
yeah, that's the previous value, which is the max.
yeah, so it will return. Adding to this, adding to this, it always be negative, right?
Negative value, more negative value.
Yeah.
Yeah.
So what you should do, you should be somewhat intelligent. So whenever getting this key right, if it is greater than 0,
Hmm.
then only add it.
Correct.
So otherwise
Go with
simply
that existing value.
add 0. Yeah, go with the existing
Mhm.
value. You can add 0. It's all about how you understand the algorithm. There is a
Mhm.
mistake we have done. So let's see what is it. Uh, Can I write this?
There is one more extra end
Yeah,
added.
greater than 0. This will also fine. Let me run it. I think some mistake we did it on that if else. Otherwise, yeah. Okay, so that way you can solve it. Perfect.
This is a pretty conceptual problem, actually.
Now let's improvise this. Now you have seen some. Now, how do you improvise it? Right? Shall we talk about improvisation?
Sure.
Okay, so let's see the improvisation. So you have 10 minus 1. Okay. Uh, what are we doing here? What are we doing here? What is the complex logic went here?
By maintaining TP and comparing with the
No,
tree
no.
set.
DP is always correct. DP you must and should need. Uh,
Tree
and
set,
with
the complex
respect to
part.
tree set, what is the complex logic you included here?
Like while inserting element, we are comparing, trying to get the last element and then
But
inserting
that
again.
is simple, right? That is constant time. Max entry is always written constant time, right?
Mhm.
The tree set I mean tree map, right? So we use tree map. So tree map algorithm, right? Tree map algorithm making it complex, right? Because it is
Mhm.
doing log k operations for the elements, right?
Correct.
We wanted to improvise that. So how do we do that? So let's move on. Let's take our favorite input. These kind of problems are will be asked in Google, bro.
Okay.
And you know, and we should yeah, for one of the round, this is not the same problem, but this is somewhat more complex than this, but some
Mhm.
kind of algorithm we should apply. And all these things you should solve in 45 minutes under the pressure of Google in your brain. Okay. So one thing for sure, when we went with TreeMap, right? When we went with TreeMap, we have adding the elements to the tree map is going to take log k operations. We want to avoid that. How do you avoid that? How do you avoid that?
if we can make sure that this lattice should be sorted already, so we can just insert the element at the end.
Sorting is always complex thing. If you sort it right, then it always, whatever you do, it always take n log n, or in this case k log
And
n.
log n time.
So you should not go with sorting, but intelligently we should apply sorting.
Okay.
Somewhat intelligent we should do. So what are we trying to achieve? Whenever you are at current element, right, you must need to know, what is the maximum element in previous window, correct? Previous
Correct.
k window, right? That's where the concept of DQ comes into picture. So let me apply the same concept. So let's say we already solved a previous problem, right? Max k in max value in the window. The same concept we will apply here. Let's see how can we do that. So this is my DP array. Okay, so this is my DP array. So I'm at 0, 1, 2, 3, 4. Okay, so 0, 1, 2, 3, 4. Initially, you know that this is 10, right? This is 10. So what I'll do, I'll also add 10 to the DQ. Okay, so 10 is present at DQ. Now, when I go to next element, I know that previous k element is valid. So whatever previous k elements are with respect to DP array, which is valid, so that in the DQ I have a top element as 10, means first get, this is first element, right? First element as 10. I pick that 10. I will add 10 plus minus 2, which is going to be 8. Now I'll add this 8 here. Perfect. This is where more critical thing will come in. So now when you are at 2, so when I'm going on 2, so I know that the previous two elements are valid, because I need to consider previous two elements. The previous two elements are already present in DQ, so that I will take that 10. I will take the first. So in the DQ, I always make sure that the first element is always going to be maximum. Okay, it always going to be maximum. If it is not maximum, if the current element is maximum, I remove it from the DQ, so that I will take care. But in this case, let's say when you are at element 10, in the DQ I have 10, first element as maximum, I blindly take the first element, so which is going to be 0. Now I am at index 3, so this is more critical part. So I am at index 3. It means the previous two elements are valid. But if you closely see, in the DQ, the first element you see, this is, of course, I forgot to add 0. So this is the I minus k wrong element, right? If the first element is equivalent to this current I, right, 3 minus k2 minus 1, so which is means DP of 0, if the first element is equivalent to I minus k minus 1 value, you delete it from the DQ. Now in the DQ I have only 8 comma 0, correct? So now if you closely see, 8 is the max value, first element is the max value, right? Add max value to this, so which is going to be 3. So now this is more important part. Now you are trying to add 3, right? So when you are adding 3, means the current element is always going to, if the previous element or smaller, you delete it from the DQ. Previous element is 0, right? 0 is smaller than current element. Current element has higher probability for future elements to come into the window, right? If it is larger, you can simply avoid previous element. Now again you will have 8 comma 3 in the DQ. Now closely see, when you are at 4, now you need only these previous two elements, right? So when you are at 4, the previous two elements are this. These are the previous two elements. Now you see I minus k minus 1. So it means 4 minus k is 2 minus 1, so which is DP of 1. So DP of 1 value is 8, which is present in DQ. Delete it from DQ. Now again you have a first element as 3, right? So 3 plus 20, which is going to be 23. So get 23 is your answer. Is the algorithm clear?
Yeah.
So it means what we did here more intelligently. It will work for duplicate elements also, because DQ allows duplicates, right?
Right.
So DQ allows duplicates. You might be thinking that if I go with 10, 0, minus 10 and 10, so initially I have 10 in the DQ, Uh, then I have again 10 in the DQ. Then again I have 0 in the DQ. When I come to this 10 will get removed. Then I'll get this 10, so I'll get 20. Correct, na?
Basically, it can contain duplicate elements. So
Yes. So there is no issue. You always remove the I minus k value. So what is the time complexity here?
order of k of the for that
Time complexity, I'm saying.
our DQ.
For
the
DQ,
DQ, space of k.
Space is DQ order of k, for DP order of n. And what is the time
Order of n.
complexity? What are you
N
doing?
into k.
Why it is k, buddy? Why it is k? You always pick up the first element from DQ, right? You are not traversing k, right?
Correct.
And also in worst case you revisit the same element twice. One
Twice.
time you add, other time you delete. Not more than 2n, right?
Correct.
It's not n into k, so it's not more than 2n, so you can say it as order of 2n. Correct?
Correct.
So that's how the DQ is the game changer here.
Yeah,
But
with DQ the complexity went down.
yeah, complexity went down, and you cannot get to that if you don't know about these solutions.
This data structure. Yeah. Without data structure we cannot go there.
Without this, it's like by hearting the algorithm if you directly go there. So what are we trying to do? So we are trying to go with DQ, correct? So DQ of integers, DQ new linked list. So what is our job? If it is greater than or equal to 0, so what is our job? We will see. So you will get old element. Okay, so old element. If it is present at our first, right? So if my DQ dot get first, if it is equal to this old element, then you can simply remove DQ dot remove first. Correct? Correct, na?
Yes.
Now let's move on. So what are we trying to do here again? We will so we need to get current max, right? So this is my current max. So what is our job now? So if DQ is not empty, same thing. So we just do that. DQ is not empty. And DQ dot whatever get first is greater than 0, then you will add this to the current max. Otherwise there is no point in adding. Correct, na? Now you will add the current max to DP, and you will, now this is the most critical part, right? So what is our job now?
Yeah.
While DQ is not empty, because we need to remove if it is not empty, and in the DQ whatever last element you have, because we need to compare last elements, right? Correct? Get last element.
Yes.
If it is less than current max, okay, not equal, buddy. If it is equal means you will remove the duplicate ones.
That mapped.
Yeah, so DQ dot remove last, and finally what you do? So DQ dot add last this current max. Correct?
Yes.
So that's how it works. It's very it's not like you by heart and do it, but it's all about the algorithm should run in your brain. Otherwise you can't write that if else logics. See, this is game changer. It went to 72%. There is
72%.
there is a somehow we did it in TreeMap, right? So same thing you can do with Heap. So the Heap also same, almost same. It was something. You love this problem. kind of this
I mean,
problem.
algorithm part kind of understood, but yeah, need to practice a bit pen and paper to get more clarity.
Yeah, yeah. It deserves hard, bro. It deserves hard, bro.
Is it a medium one here in the lit
It's
code?
hard, bro. It's hard only.
Okay, yeah, it definitely a hard one.
Okay, so let me stop the recording.